Swayam Prabha. Digital India. Educated India.
Hello and welcome. We continue with our discussion on the design of Bezier segments and curves. This is lecture 18 on composite and rational Bezier curves. But before we get into composite and rational Bezier curves, let's try to relate cubic Bezier curves with cubic Ferguson segments. There is a one-to-one correspondence between these two segments. For a Ferguson curve, the position vector is given by this 1 by 4 matrix of u cubed, u squared, un 1, the Ferguson coefficient matrix, which is of size 4 by 4, and the geometric matrix. Here you have the first point, the second point, the first slope, and the second slope. Correspondingly, for a cubic Bezier curve, this 1 by 4 matrix is the same as this one in U. This 4 by 4 matrix here is a Bezier matrix, and this 4 by 3 matrix is the geometric matrix that takes the information from the 4 design points or control points that you specify. Recall that these are Cartesian coordinates in Euclidean space. So each P will have the coordinates x, y, and z, and accordingly those coordinates are going to be placed column-wise. If these segments are to be the same, we'll have to impose an equal to sign here, and this would be true for all values of the parameter u between 0 and 1. So what we do here is we absorb this geometric information into this and come up with a resultant 4 by 3 matrix here. So the first term is 2 times p sub 0 minus 2 times p sub 3 plus t0 plus t3. The second term minus 3p0 plus 3p3 minus 2t0 minus t3. The third term is t0, that's the first slope, and the fourth term is p0, that is the first point. Likewise, we do the same here. We multiply these two matrices to get the first term as minus p sub 0 plus 3p1 minus 3p2 plus p3, 3p0 minus 6p1 plus 3p2 minus 3p0 plus 3p1 and p0. And if we now compare the coefficients of u, we will get the first condition as the slope t0 is equal to 3 times p1 minus p0. These are the first two design points corresponding to the Bezier segment. Comparing the coefficients of u square will give us the second slope of the Ferguson curve, which is represented by t3, and that's equal to 3 times p3 minus p2. These two will be the last two design points on a Bezier segment. The geometric matrix for a Bezier segment in terms of the slopes from Ferguson segment will be given by T0, the second term as T0 over 3 plus P0, the third term as P3 minus T3 over 3, and the fourth term as P3. What am I trying to say here? What is possible is the interrelation and therefore conversion of geometric matrices between Ferguson and Bezier segments. Given a Ferguson curve, you can always convert the slopes into the corresponding design points, like here. And on the other hand, if you're given the geometry pertaining to a Bezier segment, it is always possible to convert this geometry back into the point and slope information that is required by a cubic Ferguson segment, again using these two conditions. Let's now get back to our discussion on composite curves. I have been repeatedly emphasizing the concept. A composite curve is constituted by individual segments. For example, this one and this one. Each segment is a low degree polynomial, maybe quadratic, maybe cubic, not more than that. You know why this is so? This is because we need to minimize oscillations in a segment. These two segments are joined together or arranged contiguously or juxtaposed together at this junction point. So this point is common between these two segments. When I say so, I have inherently imposed position continuity. If I further go ahead and impose slope continuity, I need to ensure that the slope from this segment at this point is a factor of the slope from this segment at this point. In other words, the direction is the same for these two segments, but the magnitudes of the tangents may or may not be the same. For a C2 continuous composite curve, I need to ensure that the curvature computation from this segment is the same as the curvature information from this segment at this point. Let's try now to get into the mathematics of composite Bezier curves. Let's start with the first Bezier segment. And let's try to generalize our discussion here. Even though I have mentioned before that this should be a low degree polynomial, let's try with a general n degree Bezier segment. Likewise for the second segment over here. This is the control polyline for the first Bezier segment, given by data points p sub 0, p sub 1, p sub 2, up till p sub m. This would make this segment an m degree polynomial. M for mathematics. Likewise, this control polyline is for the second segment here. It's given by data points q sub 0, q sub 1, q sub 2, up till q sub n. N here stands for notation. This segment will be an n degree Bezier segment. Let's represent this segment r sub 1 with parameter u sub 1. U sub 1 equals 0 would mean I'm here, and u sub 1 equals 1 would mean that I'm here. Likewise, This segment is represented by R sub 2 with parameter U2. Again, U2 equals 0 makes me go here, and U2 equals 1 makes me go here. And of course, these parameters U1 and U2 are not dependent on each other. They are independent in the sense the values of U1 would not dictate the shape of the curve of this segment, and the values of U2 will not govern the shape of this segment. Let's now try to concentrate on this neighborhood here. For C0 continuity, I would want to impose that this point here, which corresponds to R sub 1 for value of U1 equals 1, should be equal to this point here, which corresponds to R sub 2 for U2 equals 0. So, P sub m and Q sub 0 should be the same for C0 continuity. Let's try to bring these 2 points together. Notice here that I'm changing this segment of control polyline. Accordingly, the second segment will change in shape, like so. Notice here that these slopes are not the same in direction as of now. We have not talked about C1 continuity or slope continuity as yet. Let's talk about it now. C1 continuity. We'll have to impose that the directions of these 2 lines should be the same and not the magnitude. This would give us additional design freedom. Mathematically, the condition is that alpha sub 1 times the first derivative of the segment R1 with respect to U1 evaluated at U1 equals 1 should be the same as some scale factor alpha 2 times the first derivative of segment R2 with respect to U2 evaluated at U2 equals 0. Alpha 1 and alpha 2 are scale factors such that these 2 terms represent the unit tangent T at this point. Recall from our discussion on Bezier segments as to how the first derivatives are computed. So, the first derivative for this Bezier segment will be m times p sub m minus p sub m minus 1 at u1 equals 1, and we retain this term alpha 1. Likewise, for the second segment, the first derivative is given by n times q1 minus q0, q1 minus q0. We retain the scale factor as well. We can use this condition to determine q1. q1 is given by lambda times pm minus pm minus 1 plus pm, which is equal to lambda plus 1 times pm minus lambda times pm minus 1. In terms of design possibilities, what would this condition mean? This condition will constrain q1. Remember that as a designer, you have so far been choosing these control points at will. If we go back to C0 continuity, Q0 here is constrained to be the same as PM. So you lose one design freedom right here. Further, if we talk about C1 continuity, this condition here constrains Q1 as well. And if you observe closely, Q1 can only be placed along this slope right here. It cannot be placed anywhere else if we are considering slope continuity at this junction point. If you do your algebra, then you will figure that lambda equals alpha sub 1 times m, the degree of the first Bezier segment, over alpha sub 2 times n, the degree of the second Bezier segment. What I'm trying to do here is graphically show you this scenario. The control polar line for the second Bezier segment changes. Accordingly, the shape of the second Bezier segment changes. The direction of the slope is common at this junction point. And now you would see the slope is same here. Let's go into C2 continuity conditions. Once again, we have seen this before in case of C2 continuous Ferguson curves. Recall this relation here. The first derivative of R1 evaluated at 1 crossed with the second derivative of R1 evaluated at 1 over the absolute value of the first derivative of R1 at U1 equals 1 raised to 3. This is the expression for curvature at point U1 equals 1 for the first Bezier segment. Likewise, the expression for curvature for the second Bezier segment evaluated at U2 equals 0 can be similarly computed. And for C2 continuity, these two expressions have to be equal. In a sense, curvature at the junction point should be unique. Let's plug in the information pertaining to the first derivatives of the two Bezier segments in terms of the unit tangent t and the scale factors alphas. So this term here can be simplified to alpha 1 squared times t crossed with the second derivative of the first Bezier segment evaluated at u1 equals 1, and this would be equal to alpha 2 squared times the unit tangent at the junction point crossed with the second derivative of the second Bezier segment evaluated at u2 equals 0. It can be further simplified to t crossed with d2 over d u1 squared of r1 at u1 equals 1 equals to alpha 2 squared over alpha 1 squared times t, the unit tangent, crossed with d2 over d u2 squared r2 at u2 equals 0. An equation that satisfies this relation here is given by the second derivative of r1 at u1 equals 1, which is equal to alpha 2 squared over alpha 1 squared times the second derivative of r2 at u2 equals 0 plus some scalar mu times the first derivative of r2 at u2 equals 0. Let's see how this relation satisfies this condition here. If you plug in the right hand side in place of this term, you'll get t crossed with alpha 2 squared over alpha 1 squared times d2 over du2 squared of r2 at u2 equals 0, which is this term. And what happens to t crossed with dr2 over du2 at u2 equals 0? Well, you guessed it right. It is 0 because the direction of the unit tangent t and the first derivative of the second Bezier segment is the same. When I say so, I implicitly assume that the composite Bezier curve is a C1 continuous Bezier curve. Let's go further. We know how to compute the first derivative, the second derivative, and so on and so forth of these Bezier segments. Let's try to plug in those expressions directly into this condition, or rather this condition here. So we have m times m minus 1 times p sub m minus 2 p sub m minus 1 plus p m minus 2, and that is equal to alpha 2 over alpha 1 the whole square times n minus 1 times q2 minus 2q1 plus q0, which corresponds to the second derivative right here, plus mu times n times q1 minus q0. We try to rearrange this relation further, and in doing so we get m times m minus 1 times pm minus pm minus 1 minus m times m minus 1 times pm minus 1 minus pm minus 2 plus alpha 2 over alpha 1 the whole square times n minus 1 minus mu n. This is a coefficient for q1 minus q0, and that should be equal to alpha 2 over alpha 1 the whole square times n minus 1 times q2 minus q1. All I have done is I have regrouped the terms pm minus pm minus 1, pm minus 1 minus pm minus 2, q1, q0, and q2 minus q1. If you go back to your figure, you will realize that these are free vectors joined head to tail in the vicinity of the junction point. We rearrange this further in terms of three vectors here. The first free vector is pm minus pm minus 1. The second free vector is pm minus 1 minus pm minus 2. And the third free vector is q2 minus q1. Notice that I am also using C0 and C1 continuity conditions to get this equation. The coefficient of Pm minus Pm minus 1 is lambda times alpha 2 over alpha 1 the whole square times n minus 1 minus mu times n. Lambda multiplies this entire term here, plus m times m minus 1. Coefficient of Pm minus 1 minus Pm minus 2 is minus m times m minus 1. And the coefficient for Q2 minus Q1 is alpha 2 over alpha 1 the whole square times n minus 1. The algebra or the expression might be looking quite complex, but this has a physical meaning. Look at this free vector, and this free vector. This relation essentially says, from the design perspective, that these three vectors, or these three free vectors, are coplanar. They have to lie on the same plane in 3 dimensions or in Euclidean space to ensure that the composite Bezier curve is C2 continuous at the junction point. Here, scalars lambda and mu are our design choices. Lambda has the same expression that we saw before, and mu is any scalar that the designer can choose. Physically, what would this condition mean? Let's go back to our figure. where our Bezier segments where C0 and C1 continuous at this point here. Pm and Q0 are the same. Now look at these three vectors, Pm minus Pm minus 1, which is this free vector here, Pm minus 1 minus Pm minus 2, which would be this vector here, and Q2 minus Q1, which will be this. From C1 continuity, we already had Q1 minus Q0 as a scalar multiple of Pm minus Pm minus 1. The fact that these three vectors are coplanar would mean that Pm minus 2, Pm minus 1, Pm, which is the same as Q0, Q1, and Q2 are the 5 design points that will have to lie on the same two-dimensional plane. These 5 points will be coplanar. From the design perspective, what would that mean? As a designer, if you had chosen these points at will, Q0 is constrained to be the same as Pm for C0 continuity. That is the first design choice that you would lose. Q1 is constrained to lie along this line here. That is a partial design choice that you lose. You are still free to choose Q1 along this line though. And Q2 now is constrained to lie on the plane defined by any two of these three vectors. Again, that's a partial loss of choice. Now for a two-dimensional composite Bezier curve, this condition is automatically satisfied, which would make Q2 as a free choice on a plane. But for a three-dimensional composite Bezier curve, this condition has to be satisfied for the curvature information to be unique at this junction point. We now come to rational Bezier curves. We have seen before that homogeneous coordinates help in unifying rotation and translation transformations as matrix multiplication operations. We'll see today as to how homogeneous coordinates can also help define individual segments more generally. In this case, a Bezier segment. Recall that Pi is given by xi, yi, zi, and 1. And if we ignore this one here, x, y, and z with indices I are the Cartesian coordinates of Pi. And Pi super h are the homogeneous coordinates, capital Xi, capital Yi, capital Zi, and capital Wi. Capital Xi is given by Wi times Xi, Yi is given by Wi times small yi, capital Zi is Wi times small zi, and capital Wi is small wi. Enough of notations. Some physical significance now. Small w sub I is the weight or scale factor. We have also seen this before, that P sub I super h and this Pi here, they represent the same point. There is an equivalence between this representation and this representation. If you think about this in a slightly different way, P sub I is the projection of P I H on the W equals 1 hyperplane. You set the small w equals 1 and you'll get back this vector here. By the way, both these are homogeneous representations of point Pi with different weights or scale factors. You must note that. Consider the definition of a Bezier segment in the homogeneous coordinate system. You have P super H as a function of parameter t with components capital X, capital Y, capital Z, and the weight or the scale here, which is also a function of t. And this is given by summation I going from 0 to n, the ith Bernstein polynomial of degree n as a function of parameter t times these design points P sub I super H. In the Bezier segments that we have seen before, we have been specifying only Cartesian coordinates xi, yi, and zi. Here we specify the homogeneous coordinates, which are given by wi times xi, wi times yi, wi times zi, and wi. From the design perspective, notice what has happened. We have introduced additional design freedom through these weights. One weight per design point that would make it n plus 1 such weights. And we will see later how this design freedom works in our favor. Let's continue with the math. Small x of t and capital X of t would represent the same point in the Cartesian space. That is what I meant. Now continuing forward, small x of t is equal to capital X of t over w of t, which is equal to summation I going from 0 to n, the ith Bernstein polynomial with degree n, which is a function of t, times wi xi over summation I going from 0 to n, b sub I super n t times wi. Try to absorb this denominator with this term here, bi n as a function of t times wi, and replace this term by br sub I super nt times xi. Retain the summation sign I going from 0 to n. Likewise, for the y coordinate, yt is capital Y over capital W, which is summation I going from 0 to n, b sub I super n times wi times yi over summation the ith Bernstein polynomial of degree n times wi. In a similar manner as above, brin is this term here over this entire term here. We'll get yi here and we'll retain this summation here. Likewise, we can compute small z as a function of t, the parameter, as capital Z over capital W. Very similar expressions. The only change is this Zi And this is given by summation I going from 0 to n b r I super n as a function of t times zi. Formally, br sub I super n as a function of t is given by wi b sub I super n. These are the original Bernstein polynomials with index I and degree n over summation I going from 0 to n wi and the ith Bernstein polynomial right here. You can think of br sub I super n as rational Bernstein polynomials. Notice that like the original Bernstein polynomials, they too are barycentric. Recall again what I mean by barycentric. That these coefficients or weights associated with the Cartesian coordinates, or in general the design points, are all greater than 0 and they sum to 1. These are greater than 0 if we ensure all these weights are positive, and we already know from before that these Bernstein polynomials are greater than 0. The second aspect of being barycentric is that no matter what t is, the rational Bernstein polynomials will always sum to 1. And that is something that you can easily observe. Try to add all these terms together. When you're done adding, what you would notice is the numerator is the same as the denominator. They would cancel out and the result will be 1. As I said before, by additionally specifying the weights small wi, we give more freedom to a designer in that he or she can now choose these weights independently and as additional parameters. Let's take a look at the example and see how the change in weights would affect the change in the shape of a rational Bezier curve. Let's start with 4 control points, P0 as 0, 1, P1 as 5, 9, P2 as 7, minus 2, and P3 as 10 and 6. We'll compute the rational Bezier segments for different weights, but to start with, we'll set all weights equal to 1. Again, realize that each weight is associated respectively with each design point here. We'll later alter the values of W2 to realize the change in the curve shape, and maybe also look at what happens to this shape of a Bezier segment if W1 is changed. Well, algebraically, this is a 2-dimensional Bezier segment. So the x component is given by W0, 1 minus t the whole cube times x0 plus 3 W1 t 1 minus t the whole square times x1 plus 3 W2 t squared 1 minus t times x2 plus t cubed x3 over W0 1 minus t the whole cube plus 3 W1 t 1 minus t the whole square plus 3 W2 t squared 1 minus t plus t cubed. This term is only slightly different than this term. Here, the x's do not appear. Likewise, for yt all you would need to do is replace x i's with y i's, and that's it. Let's look at how rational Bezier segments change in shape. P0, P1, P2, and P3 are our original data points. The lines in black show the original control polyline. This curve is a cubic Bezier curve when all the weights are set to 1. Let's try to play with the weight corresponding to this data point, which is W1. If I increase the weight W1 to 3, I get the blue segment here. Observe the change in shape. This region of the curve has moved towards this data point. In other words, if I had increased the weight associated with P1, point P1 has attracted the curve towards itself. Let's confirm this. If I increase the weight W1 from 3 to 10, I get this green rational curve. Notice what has happened. P1 has significantly attracted the curve towards it. Let's now see if the same is true if I raise any other weight. Now, if I keep W0 as 1, W1 as 10, W3 as 1, and if I raise W2 to 10, I get this curve in magenta. Now, P2 has attracted the curve towards it. The point that I'm trying to make here is, had we considered only a Bezier segment and not the rational Bezier segment, with the same control polyline, I could not have changed the shape of the red curve, which is our original cubic Bezier segment. With the addition of these weights, keeping the control polyline the same, I can now play with the shape of a Bezier segment by merely changing these numbers or the weights. As I increase the weight corresponding to any data point, the curve will gravitate towards that data point. Features with the rational Bezier curves. You would realize that we have more design freedom when modeling rational Bezier curves. This is because of the additional weights that we assign along with the data points or design points. This is something that we are going to be discussing a little later, but through rational Bezier segments, we acquire the ability to model conics precisely. Precise modeling of conics cannot be done with polynomial Bezier segments with even higher degrees. We still have this problem of no local shape control with rational Bezier curves. In a sense, if you move or relocate a data point to any other position, or if you change the value of any weight, the entire shape of the segment changes. Let's discuss now how to model conics with rational Bezier segments. But before that, let's brush up our concepts on conics. Let's say we have a point, and let's call it focus F. Let's assume that we have a line that does not pass through this point here, and let's nomenclate this line as directrix and denote it by D. Let's sketch another point, P. Let's measure these two distances, the distance between P and the focus and the perpendicular distance between P and the directrix. Let's call them D1 and D2 respectively. These distances will have a ratio. D1 over D2 equals E. Let's call E the eccentricity. A conic will now be a locus of all points P for a constant value of eccentricity E, like so. In other words, all these points on this curve will be such that the distance between any point here and the focus over the distance between that point and the directrix has a constant ratio, the eccentricity E. Let's look at a few cases. We have the focus F and the directrix D. This directrix again is not supposed to pass through this focus. For the circle, which is a conic, we have the eccentricity value equals 0. For an ellipse, the eccentricity value will be anywhere between 0 and 1. For a parabola, E is equal to 1, and for a hyperbola, E is greater than 1. Let's use this concept and try designing conics using rational Bezier segments. Let's consider a quadratic rational Bezier segment defined by 3 data points P0, P1 and P2. Let's sketch the corresponding control polyline. This would be a quadratic rational Bezier curve. If I also assign weights W sub 0, W sub 1 and W sub 2 to these corresponding points. Let's join P sub 0 and P sub 2. Let me also draw a line parallel to P0, P2 here, which passes through P1. And from P1, let me draw a line that intersects P0, P2 at point D. Point D is the midpoint of the segment P0, P2. In other words, P0D is half of the distance P0, P2, and likewise D, P2 is half the distance P0, P2. We'll consider D as the focus and this line here passing through P1 as the directrix. Let's take a point P on the curve and let this point correspond to the parameter value half. Now we are going to be choosing a quadratic rational Bezier curve in a slightly different manner, in the sense that we'll have the weights corresponding to P0 and P2 assigned as 1, and we'll have the weight corresponding to P1 assigned as W that we need to find. So this is how a quadratic rational Bezier segment will look like. The position vector P, which is a function of parameter t, will be 1 minus d squared P0 plus 2 W, which is the weight corresponding to P1, times t times 1 minus t times P1 plus t squared times P2 over 1 minus t squared plus 2 times W times t 1 minus t plus t squared. Once again, the weights corresponding to P0 and P2 are 1, and it is this weight W which is associated with P1 that we need to determine. For midpoint P, that is for t equals half, we get P equals P sub 0 plus 2 times W times P1 plus P2 over 2 times 1 plus W. Let's compute the distance dP. But first, the vector dP is given by the position vector of P minus that of D. If we work the algebra, it is equal to P sub 0 plus 2 times W times P1 plus P2 over 2 times 1 plus W minus half of P0 plus P2, which is point D here. On simplification, this expression becomes W times 2 P1 minus P0 minus P2 over 2 times 1 plus W. Now, the distance PP1 would be the magnitude of the vector PP1 here, which is P1 minus P, which is equal to P1 minus W times 2P1 minus P0 minus P2 over 2 times 1 plus W. Upon simplification, that is 2 times P1 minus P0 minus P2 over 2 times 1 plus W. All we need to do is we need to compute the magnitude of dP and that of PP1, compute the ratio, and equate it to the eccentricity E. So, the absolute value of dP over the absolute value of PP1 equals W. Let me go back. Notice that these terms are the same here. If I divide the absolute value of dP over PP1, these terms cancel out and these terms cancel out, and what is left is W here. So, absolute value of dP over absolute value of PP1 equals W, and which is the eccentricity of the conic. Clearly, from the definitions that we have seen previously, for values of W or eccentricity smaller than 1, we get an elliptic segment. For W equals 1, we have a parabolic segment, and for values of W greater than 1, we get a hyperbolic segment. In a sense, all one would need to do is specify P sub 0, P sub 1 and P sub 2 arbitrarily and set different values of W to get different conic sections. How about modeling circular arcs with rational Bezier curves? Here's a figure here. We have a circle with center O and 3 points P sub 0, P and P2 lying on the circle. This curve here represents the circular arc, and it's modeled, let's say, as a quadratic Bezier curve again, defined by the control polyline P0, P1, P2. P here corresponds to the parameter value t equals half. Let's try to work the algebra to see if we can get a circular arc. The method here is slightly different from what we had discussed a bit earlier for other conic kinds. Using trigonometry, we have OP1, this distance, is equal to OP0 over sine theta, this angle here. Notice that P0, P1 is a tangent to the circle, and so this angle is 90 degrees. Now OD, right here, is OP0 sin theta. Quite straightforward. DP1 which is this distance here, is equal to OP1 minus OD, which is equal to this term here minus this term here, taking OP0 common out, rather the magnitude of OP0 common out. The remnant terms are 1 over sine theta minus sine theta. How about dP, this distance here? dP is given by OP minus OD. OP is the same as the radius of the circle, which is OP0, and OD is what we had obtained before, the radius of the circle times the sine of theta. On simplification, the absolute value of dP is OP0 times 1 minus sine theta. Now, we have this distance dP here. We are assuming that D would act as the focus. The absolute value of dP over pp1 is equal to the modulus of dP over mod of dP1 minus mod of dP, dP1 minus dP. dP is given by the radius times 1 minus sine theta, and dP1 minus dP is given by the radius times 1 over sine theta minus 1 plus sine theta. The radii terms get cancelled out, and this expression gets simplified to sine theta, which is the eccentricity, and from previous slide, that is equal to the weight corresponding to P1. In other words, if we assign the weight W0 and weight W2 as 1, we will need to assign weight W to P1 such that W is equal to sine theta, but theta is this angle, which is also the same as this angle. This would ensure that this point P corresponding to T equals half lies on the circle, defined by 3 points, P sub 0, P and P2. Let's try to solve this example in a slightly different manner. So given data points P sub 0 as 1, 0, P sub 1 as AA, and P sub 2 as 0, 1, we will determine the circular arc using rational quadratic Bezier curve for different values of A. First, let's talk about the included angle, theta. Since these two triangles are congruent, this angle is the same as this angle. So 2 theta is the inverse cosine of the dot product of these two vectors, which is P2 minus P1 dotted with P0 minus P1 over the absolute values of these two vectors. We can work the algebra out, and we'll find that 2 theta is equal to the inverse cosine of minus 2a times 1 minus a over a squared plus 1 minus a squared. We can use this angle directly to compute this quadratic rational Bezier segment depicting an arc of a circle. All we need to do is assign the weight corresponding to P1 as sine of theta, which is this angle or this angle here. Alternatively, what we can do is we can compute the equations of the lines containing the center O. One of the lines is given by y minus 1 equals a over 1 minus a times x, and the second one is given by 1 minus a over a times x minus 1. All we need to do is either find the equations of these two lines and compute the intersection point here, or maybe find the equation of this line and this line, compute the intersection point. How would you get the equation of this line? Notice that OP0 is perpendicular to P0, P1, and you would already know the equation of this line because you know the coordinates of P0, which are 1, 0, and P1, which are AA. The slope of OP0 is minus of 1 over the slope of P0, P1. You should be able to work out the algebra. Anyhow, the coordinates of the center are given by 1 minus a over 1 minus 2a. This is the x coordinate. 1 minus a over 1 minus 2a. This is the y coordinate. And the radius of this arc is given by square root of 1 minus a squared plus a squared over 1 minus 2a the whole square. This is an example for a equals 0.7. The blue segment here is the quadratic Bezier curve, which is lying precisely over this dashed magenta circle.